Hey kiddos. Happy week 5. This is a recording of the lesson that was presented in class this week on Monday during our live class session. Okay. Our goals today are to apply Kirchhoff's rules to circuits with multiple loops and multiple power supplies. All right. So again, these are rules that apply not for series circuits, not for parallel circuits, not for complex circuits, but for circuits with multiple power supplies. Okay? There are two rules. One is called the junction rule, and one is called the loop rule, and I'm going to read them, and then I'm going to interpret them, okay? So the junction rule says the sum of the magnitudes of the currents directed into a junction equals the sum of the magnitudes of the current directed out of a junction. Okay? So really what this is saying is if you had two currents going into a junction, right? I1 and I2. A junction is just a place where two currents or two wires connect. If you have two different currents running in two different wires and they connect at a point, and then their only option is to go into one individual wire, it's saying that the magnitude of the currents directed into a junction is equal to the total magnitude of the currents directed out of the junction. So if current 1 and current 2 combine at a junction, the magnitudes of their current will be equal to the value of current 3, the current in the wire that they're connecting to. Okay? And again, junctions are just places where wires connect, where multiple wires connect into one wire, or one wire splits off into multiple. Okay? The second rule is called the loop rule, and that one's a little bit more conceptually complicated, and it says around any closed circuit loop, the sum of the potential drops equals the sum of the potential rises. Okay, so remember, we said that power supplies typically provide potential rises, potential gains. They give electrons energy to flow within a circuit, and it's resistors like light bulbs, resistor devices, power supply, or appliances that provide potential drops or resistance. Okay, so this is just a kind of an abbreviation of the law of conservation of energy, where all of the energy put into the system is equal to all of the energy used in the system. So all of the potential gains are equal to all of the potential drops. All right, let's take a look at an example. And this is an example from the Cutnell and Johnson textbook. And again, sorry, I've got kind of a pixelated copy from this. What you'll notice here is you've got two power supplies right here and right here. One is 6 volts and one is 24 volts. You also have two resistors in the circuit. Okay, so conveniently in this circuit there is only one loop and there are no junctions, right? There are no places where wires connect or wires split off. And some of the current can go its separate ways. We've just got one loop. Okay, so in when using Kirchhoff's rules, it's important to kind of label corners of where there are junctions or where there are corners to describe what loop you're going to go around. So let's say this is loop A, B, C, D. They labeled A right here, and so I just kind of went around clockwise. Okay. So if we say that we're working around loop A, B, C, D, the next thing that we need to do is draw, like physically draw in our current in that direction. So we say we've got current going around A, right? Around A, B, C, D, kind of going around in that order, A, B, C, D. Okay. So I like to draw a little current arrow next to each of the power supplies and each of the resistors. Okay. Now let's follow that current in the order, and we are going to determine what side of the resistor and power supply are the high and low potential ends. And that will help us figure out whether a device is providing a potential drop or a potential gain. Okay. This is where it gets confusing. Okay, so we're going to start right here at corner A, and we're going to follow the current through the loop that we are predicting. Fun fact about this rule, we just need to predict a direction of current flow and use our conventions, pretending like current is flowing through that direction. That might not be the real direction that current is flowing in the circuit. Okay? But we need to pretend like it is, and then the math will tell us if that is real or not. Okay, so let's start here, and we will do loop A, B, C, D. Okay, so we're going to apply the loop rule, and here's the thing with the loop rule. We need to set the potential gains equal to the potential losses. Okay, so I kind of set up an equivalence here. All right, so if we're going around in the direction of from A to B to C to D, the current would go to the right in this top section through a resistor, and we'll assume that resistors do what resistors do, and they provide a potential drop because we're starting out at a high potential region and going to a low potential region. Okay, so if we're going from positive to negative or high to low potential, that resistor will provide a potential drop, and that's what we're assuming is happening. So how do we provide a potential drop? Well, we've got V equals IR. So there's one current we're calling I going through the circuit, and the resistance of that particular resistor is 12 ohms, right? So multiplying that current times the resistance will give us the value of that potential drop. We don't know what the potential drop is or the value of the current, but you were using this tool to help us figure that out. Okay, so that's the potential drop provided by that 12 ohm resistor. Okay, then we will continue going around this circuit, and we'll go through this power supply. Now, here's the problem. This power supply, in the direction that we have defined that we predict the current is going, the current is going to go backwards through the power supply, right? The high potential side is on the left, the low potential side is on the right, and we are going to the right. So this is a drop, right? Just like this. That's a drop. So we are going to put this on our side of potential losses. Okay, we've lost some potential due to our resistor. We're going to lose 6 volts of potential by going backwards through a little power supply. Okay, and then we'll go down here, go through this resistor. Okay, and in the direction of our current, resistors are going to do what resistors do. And we will go from high to low potential, and we'll have another potential drop that's the V is equal to I times R, and here the resistance is 8 ohms. Okay, so we've had some potential drops. Now the last thing that we'll do to complete our loop is go through this power supply, and this power supply is oriented where our current is going to go from low potential to high potential. So this was a drop, but this is a gain in potential, and it's 24 volts, and so we're going to write that down as our only potential gain here. All right, so now we've got an algebraic equation where we've got this is how much potential is put in, and all of this on the right hand side is what was lost. And so we're solving for I here. Okay, so we get 24 volts minus 6 volts is 18 volts equals, on the right hand side we have I times 12 plus I times 8. So we get I times 20, right? And then we can solve, and the current flowing through this is 0.9 amps. Okay, cool. All right, let's take a look at one more example from the Cutnell and Johnson textbook. Zoom out a skosh here. All right, so on the left is what the circuit diagram on the right is trying to represent. Okay, so what we have up here is a headlight. That headlight is providing resistance in the circuit, okay, of 1.2 ohms. Okay, connected to that is a battery. A battery has some resistance in it, and it provides some potential difference. Okay, so that's the middle segment of our circuit. Okay, and then finally, there's an alternator. And if you've ever worked on a car, you know that the alternator is the thing that the engine runs to charge your battery. Okay, so you'll notice the alternator, the positive side is connected to the positive side, and the negative end is connected to the negative end of the battery in an effort to charge that battery. Okay, so this is the alternator, battery, and then the headlamp is what's going on in this circuit. So we've got 3 resistors and we've got 2 power supplies. Okay, so our first step is to decide what direction current is, we predict current will flow in each section of this circuit, in each segment, in each individual wire. Okay, it's drawn in here, but think about whether you predict that that makes sense. And I'll meet you back here in part B of the video.